Alright, let's say you check the flood switch as you did in part 1 of this video series, and your float was good, your thermistor was good, it was all in spec, and it looked good. So where do we go now? Well, now we're going to go a little deeper. We're going to be pulling out the dishwasher. So the first thing we want to do, let's turn off the power. So in my case, it's circuit breaker number 24. So we turned it off. So the power, electrical power to the dishwasher is off now. Now, depending on how long your water supply line is and your drain line, you may have to disconnect those. In this case, my drain line and the water line is long enough. But in my case, you would have to come over here, disconnect it, and then you may have to just pull the whole drain line out with the dishwasher. And same goes for the water valve. So if you want to be sure to also turn off your water valve also. Depending on what kind of countertop you have, in my case I have a laminate countertop. So usually you're going to find some straps here with a couple of screws. One is over here and you got another strap here. Now if you have a granite top or a marble top or quartz top or some other synthetic top, usually what's going to happen is they're going to be mounted here on the side. You're going to have a strap here or here, so you'll have some holes, and then you'll have to be securing it on the side of your cabinet. One over here, a couple of screws over here. So anyway, I'm going to remove these 2 screws and then I'll catch you in the next shot. Once I got the 2 screws out, then we can just kind of wiggle this thing right on out. Alright, so here's our water inlet valve. So maybe you're not having enough water coming in or no water at all. So let's say we want to check this valve out. Alright, so here's what we're going to do. We're going to take a look at our little diagram. Now we can see that here's our water inlet valve. We can see that it's going to take 13.5 volts DC. And on the coil for this here solenoid, it's going to be 32 ohms. Now I would like to know what kind of amperage is that going to be. So using a little bit of Ohm's law, we'll take 13.5 volts and we're going to divide it by the resistance of 32. And we see that we have about 0.42 amps. So let's go ahead. I got the amp clamp set up here for DC amps. And I'm just going to grab this here orange wire. Doesn't matter, it's got an orange and a gray. I'm going to hook around the orange. And then we're going to start it up. And we're going to let the water come in and let's just see what kind of amperage we're getting. Of course, we're going to have to turn the power back on. We turned it off for safety reasons, when we're pulling it out, because you never know where the cable is at, and that way you can look at it. But now that we know everything is safe, we're going to turn it back on. Now let's go back over to the water inlet valve. Okay, so I'm going ahead and I've got it on a normal cycle, and I'm just going to go ahead and hit the start button. Let's just see what we get. Okay, 0.47, 0.46. That looks good to me. I can hear the water going in, so that all looks good. Okay. So now what we're going to do is I want to go ahead and I want to cancel this. So I'm holding the button in for 3 seconds, and then the drain pump's going to start and it's going to remove the water. And of course you can see the solenoid is turned off because we have 0 amps. Alright, so let's take a look at this here voltage across the water inlet valve. Alright, so if we go and follow this here back, we can see it all originates right up here on J711, which is the header pin connector that's located on the main control board. Now we're starting off with 13.5 volts DC, so when the dishwasher is calling for water, it's going to put this voltage here on terminal 1. It's going to go through the connector. It's white with a red tracer wire. It's coming all the way over here. Now this here is the header pins and the connectors for the flood switch, right? And that's going to go to terminal 1, and we've looked at that in the first video. And then we're going to go through a closed float switch. Now this float switch is closed when there's no water in the tub. Then it's going to come through internally inside the sensor, coming back out on terminal 7. And then it's going to turn to an orange with a gray wire, and it's going to go to feed one side of the solenoid. And then the DC negative return is going to be a gray wire, and it's going to come all the way back to terminal 2 on the J711, which I said is located on the main control board. Now, what we're going to do here is a little experiment. I have this here connector unplugged, so my voltage will probably be a little bit higher, and it will probably have some floating voltage there, even when it's not calling for water. But what my theory is, and this is where I think it works, is that when this here is calling for water, the 13.5 volts is going to come through the switch, the float switch, and it's going to energize this here solenoid. Now, since I have it unplugged, this here is not going to allow any water in, which means that this float is not going to never change state. So it's always going to remain closed. So what I think what's going to happen is there's an internal timer in the microcontroller. In fact, I think it's about 5 timers in it. And this here timer is going to time for 60 seconds. At the end of 60 seconds, then this here voltage is going to disappear, and then that's going to drop out the voltage that's over here. So that's what we're going to look at, and I'm going to set a timer to verify that. So it's just new for me, but I think that's how it works. Now you might be asking, well, why not just have this here float switch, you know, to get to the water level it should be, it opens, and then it just cuts off the circuit to the water solenoid. Well, the reason for that is it's called a flood switch. What happens, say, you're going to drain, you get ready to drain, and for some reason the water won't drain, your pump is locked up, maybe a piece of glass in it, or your drain line is stopped up, and then that water is still inside the dishwasher. Well, so it thinks it's drained the water. Now here comes the next water cycle to raise the water level, and when it does that, that is going to open this here switch to prevent a flood condition. So once this opens up, even if the timer is still going and you're still providing 13.5 volts to the float, since it opens, then that's going to turn off the solenoid. So you can think of this float more or less as a backup safety condition, so you don't have a flood condition with way too much water inside the dishwasher. So let's get ready to do that experiment and see what it looks like. All right, getting ready to start the dishwasher. All right, I just started it, and I'm starting the timer. Now you can see on the connector for the water inlet valve, you can see we got our 14 volts, and we're setting our timer. So basically, we know the float is not going to raise because no water is coming in it, so the float is closed. So what we want to look at is that after 60 seconds or thereabout, is that voltage going to disappear. Now remember, we're disconnected from the solenoid, so we're going to have like an open voltage, so it might rise 3-4 volts, something like that, so it's not going to go all the way back down to 0. But what we're looking for is for that 14 volts to kind of drop down in voltage, and we'll see what's going to happen here. There you go. So now the circulation pump you hear started, but of course there's no water in it, right? So I'm going to go ahead and I'm going to stop it. And now you can hear that when I canceled it by holding the start button in for 3 seconds, that stopped the circulation pump, and now you can hear the drain pump. You can hear now it's running, but of course there is no water in the system. Now let's say you did these checks and everything looks good. You had amps on there, so you know you got continuity through your windings. Of course, you could check the resistance of the winding if you want to. That's going to be about 32 ohms, as I mentioned in the first video. But you're still not getting no water. Well, if you got your voltage there, like you saw earlier, then you know your float's good, and you checked that earlier when you did it in the first video. You checked it with the ohm meter. You got your 13.5, 14 volts. Then you got a problem with the solenoid. Some trash is in there or something like that. So go ahead and replace the solenoid. Another thing you can do, you can see right here, this is the outlet of the water for the solenoid. So this hose is going up, and this is taking the water into the, into the dishwasher. Now, if you want to, you could disconnect the line here, and you can see if you're going to get see how much water comes out. Maybe you got a problem with the water supply line coming into the dishwasher, but more than likely you'll have a problem with your solenoid if you don't have any water coming into the solenoid, into the dishwasher, if all these checks, all confirmed and okay. All right, now the next thing we're going to talk about is this thermistor in this circuit. It's probably it's not difficult, but probably for some people it might be a little harder to understand than a simple switch, and a timer operating a solenoid. Alright, as I mentioned earlier in the first video, the thermistor will change its resistance based on the temperature. Now this is the NTC type thermistor. That means negative temperature coefficient. That means as the temperature goes up, the resistance will go down. Alright, vice versa. So let's look at it. We follow it back. We see that it again is coming off of J711. That's off the main control board. We see it's coming off of terminal pin 6 here. Now I did some calculations. There's going to be another resistor ahead of this thermistor here. For my calculation, it's around 4,760 ohms. Now that's 5 volts DC that's being fed to this resistor, goes out, feeds the thermistor, comes back on the other side of the thermistor, comes back, and it goes to DC return for the 5 volts. Now I pulled this here table up for the thermistor specifications, alright? Now I want you to take a look. It says voltage. Well, where is this voltage measured? Where is it measured across or whatever? Now look at here. We have this 20,066 ohms. And we got 0.95 volts. And as this here resistance is decreasing, right? Now this is the resistance for the thermistor. Notice that the voltage is increasing. Well, that can't be right. From Ohm's law, we know that as the resistance increases, the voltage should be increasing. Okay, so that's one thing that we notice. Now I pulled another one up from another model. We have the same thing. Okay, well now it's telling us DC volts, but it's exactly the same thing. Okay, well let's go over here. Now we're getting somewhere. Now this one says input voltage. Well, that makes a little more sense, to what we're seeing. Because now we can see that as the resistance here, right, is decreasing across the thermistor, we can see that the voltage is rising, right? So we know that this voltage here is not across the thermistor. This is across a fixed resistor. As I mentioned earlier, you can see that we have the 5 volt DC. So let's break this circuit out a little bit. We have our 5 volt DC. It is feeding a resistor, fixed resistor value. I calculated it to be about 4760 ohms. Now this here resistor is located on the main control board. Now you can see that it feeds and comes out. It is feeding one side of the thermistor, so let's draw that. And then you can see that the other side of the thermistor is going back to DC negative. That's the 5 volt DC negative return. So let's put that there. And let's call this the thermistor as a reminder. And then here's our fixed resistor value up here. Now this here value can change, and let's just look at our table over here. And it can go from, let's say 20K down to 1.3K. So we'll put 1.3K ohms up to, say, 20K. Let's say that's a normal range. That this value of resistor, or thermistor, this value can change depending on what the temperature is that is sensing. And again, now this one doesn't change. That kind of stays fixed. Now let's take a look over here. We can see that we have a line coming off of the 5-volt DC, and it's going to, this is the measured volts to a 10-bit by 12 channel analog to digital converter. So let's draw that. So one side is coming off to the 5-volt supply. Then we see that the other side is coming to right here. Now this right here is going to that 10-bit analog to digital converter. Now this analog to digital converter is inside the microcontroller. Now as the resistance changes on the thermistor, the voltage that's dropped across this resistor will change. And when this voltage changes, the voltage that's across this fixed resistor is also going to change. Now let's take a look at an example. Let's say that we had 1.3K. In other words, the resistance across this was measuring 1.3K. Now if we come over here and we look at, well, what is the resistance across the thermistor? And let's just round it off and let's just say it's 1 volt. So if I put my voltmeter across here and here, I would measure 1 volt. Well, how many volts would be dropped across here and here? That would be 4 volts. 4 and 1 is 5. The voltages, and you notice that is equal to the source voltage. So, and that's from Kirchhoff's law. Voltages dropped across resistors in a series circuit must add up to the source voltage. So if this was, say, 2 volts across here, that means this voltage across this resistor would have to be 3 volts. 3 and 2 would be 5 volts. Okay, using our example of 4 volts and 1 volt, so the analog to digital converter is going to be looking at 4 volts. That's what's going to be coming into the 10-bit A to D converter. Now, the computer, the microcontroller, or the CPU, it cannot directly look and handle a 4-volt analog voltage. So it has to take this voltage and it's going to convert it into ones and zeros that the microprocessor can handle, and it'll take that value and store in a register inside the CPU where it can be processed, and you can do your programming on it to whatever you want to do with that value. Now let's take a look and let's see about bits. Now to start off simple, we're not going to go full blown with the 10-bit. Let's just say we had a 4 bits that we're using. So let's say I had 0, 0, 0, 0. So there's all the zeros, right? So that means that this number here in decimal, that's decimal 0, because in computer science, and when you're looking at binary numbers, and this is a binary system where it converts these ones and zeros, and it's bi meaning 2, so your only possible values is a 0 and a 1. That's all you can use to represent any decimal number that we normally count in, like 1, 2, 3, all the way up to wherever. All right. Now I'm going to show you how we can convert this here 4-bit numbers, right? And we're going to start off on the far right, and that's going to be 1. Then we're going to double 1, we're going to get 2. Double 2, we get 4. Double 4, and we get 8. So if I want 0, what do I write down here? I write, well, it'll be all zeros. But now here's where you can get to where we're at. Well, our next number we're going to count up with is going to be 1. So looking at these here, 1, 2, 4, and 8, what number do I need? And if I need that number to represent 1, I will put a 1. Well, do I need an 8? No, I don't need an 8. How about 4? No, I don't need that. I don't need a 2. Hey, I do need that 1, so I put a 1 right there. So I go to 2. What do I need for 2? Well, look, there it is right there. I don't need any of these. So that number, 0010, is going to represent the decimal number 2. All right, so let's kind of go ahead right on through them. So you can see I put 1, 1 because I need a 2 and a 1. 2 plus 1 is going to give me 3. So if I go to 4, what do I need? Well, look at there, there's 1. I don't need any of these other ones, so I go to 5. What do I need for that? Well, I need a 4. I need a 1 over here. 4 plus 1 is 5. There's my zeros, don't need them. Now if I'm going to do 6, then I'm going to do this one and this one, 4 and 2. And then we're just going to keep right on down. Alright, so 7, I need this. 8, I need this one. Don't need any of them. 9, okay, I need that one. I need that one. I need that one, right? 8, 2, 1. What is that? Oh, that is not right. That is not right. See? Did I do that on mistake so you can catch that? No. So we need an 8, we need a 1, and then we don't need these.
Yeah.
Now we do 10. I need an 8 and a 2, so let's put down a 1. Don't need a 0. Need that one. Need that one. 11. I need this one. I need this one. I need this one. I need that one. And then on 12, let's see. I need that one. I need that. Don't need them. And then on 13, what do we need? We need that one, and that one. And then on 14, what do I have? 14, I need this one. Don't need that. Well, yep, I do need that. Because 8 and 4 is 12, right? And 13, 14, so I need that. And here we go. And on 15, I need that, and that. All right?
Okay.
Now look how many numbers I have. I have 0 to 15. How many numbers is that? 0 to 15. That's 16 numbers, right?
Yeah.
16 numbers. So I can represent 16 numbers, right? For using 4 bits. See? 1, 2, 3, 4 bits. So I can represent 16 numbers.
Okay.
Now let's get back over to our 10-bit. 10 bits. That sounds like that's going to be a lot of numbers that we can represent. So, what do we do? Let's flip over. How do we figure out how many numbers we can represent with any number of bits? Well, this is how it's done. You take 2. Why 2? Because we're using base 2, the binary system. And all we have to do is raise that number to the number of bits. Well, you have 10 bits. So, let me get my calculator. Alright? Got my TI-89 calculator. This is what I used when I was going to university working on my electrical engineering degree. Great calculator. Alright? Hopefully you'll be able to see this. So I'm going to put in 2. Alright? I'm going to raise it to the 10th power. As you can see, I have 1,024 different possibilities. But now here's the thing. Remember I said earlier, everything starts with 0. So the range of numbers that I have is from 0 to 1023. So all you have to do is subtract 1 from whatever your highest range is. So this is the number of possibilities you have. It's 1,024. You subtract 1, and that'll give you 1,023. Because remember, we're starting from 0 to 1023, and that's a range of 1,024. Okay? Okay, so now that we know that, we want to know for every bit change, what is the resolution of how much would the voltage change for every bit change? Well, what we do there is we put down 5 because we're working with 5 volts. It's the 5 volts that's supplying the circuit. Then we're going to divide that by what is our maximum amount of bits that we have to work with, or our numbers to work with. And that's going to be 1,024. Okay? Now, let us say that we want to know what would be the bits for the number, I don't know, let's just say 1.25 volts. And what you're doing is you're taking your 5 volts and you're putting it right across over here. Well, we want to know what number will be expressed for that 1.25 volts. Well, that's going to be, we don't know. So if we take 5 times x, we're going to get 5x. And if we take, and we're doing a cross multiply. So now if we take 1024 times 1.25, and let's see what we got there. So if I take 1024 times 1.25, I am going to get, looks like 1,280. If you look on the calculator, I've got it set to express in engineering format. So that's 1.28 times 10 to the third power. So what I'm doing is I'm just taking the decimal point and I'm moving it over 3 places. So it'll be 1280. Now to find out what this here x is that we're looking for, we're going to divide both sides of the equation by 5. So they cancel out, leaving us x. So now we'll just take 1280 and we're going to divide that by 5. And that's going to give us 256. Now that is what's going to be expressed. That's the decimal value. But what is it going to be actually in the A to D converter that the processor is going to be used? Now, since we showed you the little example about how to use a 4-bit number, we're going to take this. We're going to start off with 1 at the far right, and then we're going to double each time. 1, 2, 4, 8, 16, 32, 64, 128, 256. All right, and we do 512. Now, is that 10 bits? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Yeah.
What do I need? Put a 1 down to give me that 256. This turned out real easy. So I put a 1 down, right? Don't need anything else. So we're going to write our zeros. And this right here, if you had 1.25, if this was 1.25 volts, right here, and then what would this voltage be? Remember that this voltage has got to add up to this when you add them together. So that means this voltage should be
375.
Let's see, 1.25, and that means this voltage across the thermistor, 3.75 volts. All right, let's take a look at this table. Now I put some more information in this table that you saw earlier. That's all you will see in the service info. All right, let's look at a condition where it's the resistance of the thermistor was open, or if it was shorted. Let's take a look at it if it's open first. Alright, so I drew a diagram. So this is all correct. No problem there. This is good. Okay? Now let's take a look at this one where the thermistor is open. So I put a break. This is our thermistor down here. So I put a break in it to show that it's open. What is going to happen? What is this voltage going to be seeing up here by the A to D converter? Well, we got our 5 volts up here, right? So that makes sense. Well, when we come down through here, what kind of voltage do you think we're going to have right here?
5.
Exactly. It's going to be 5 volts. Now, when I put my voltmeter leads right across here, if I got 5 volts here and I got 5 volts here. Now, voltage is sometimes called potential difference. Now, difference means subtract. So when you're measuring voltage, you're always measuring from one point in reference to another. So what it's going to do is going to take, the voltmeter is going to actually take this voltage and it's going to subtract. So what you're going to see on your voltmeter is 0 volts. All right. So if you look over here, this is what's going to be going up to the main board. So the A to D converter is going to see 0 volts. Well, do you remember when I said if this is 0 volts, how many volts would have to be from here to here if I measured across the thermistor?
5.
Right, because 5 plus 0 has to equal this. And another way to look at it is there's a 5 volts across the thermistor. So another way to look at it is that if I was to have say my 5 volts, we know the 5 volts is going to just pass right on down through here, 5 volts. And then this is going to be 0 volts because it's referenced to ground for a DC negative return. Now if I take 5 volts and subtract 0 volts, I get my 5 volts. Now finally, let's take a look at it. What happens if the thermistor was to be shorted? In other words, we have like very near 0 ohms. All right. Again, we're going to have our 5 volts up here. No problem there, right? But when we come down, and if we look over here, this is our ground. This is our 0 volts. Well, here's our thermistor, but it's shorted. So it's just like a straight wire. So that 0 volts is going to be right here. So look again, 5 volts subtract 0 volts. What is that going to be across here? 5 volts. And if we come down to here, 0 to 0, subtract, going to be 0. And that adds up, 5, 0 equals 5 volts for our source. And again, if we look over here on the table, down here at the bottom, shorted, right, 0 ohms. And if I look here, the voltage that's going to the main board for the A to D converter is the 5 volts that we just said. And if we measure across the thermistor, we're going to get our 0 volts. Alright, so since we covered about the condition of where the thermistor is open or shorted, let's look at that and see how is that taken account of inside the program. Well, obviously, we do not want to see 0 volts coming in, because if we're looking and monitoring this voltage and we get 0 or very near 0, we automatically know that the thermistor is open. So what do we do in a condition like that? Okay, when we see that kind of condition in a program, we could say, okay, blink a certain light to represent that the thermistor is open. Do we want to turn on the heater? Absolutely not, because we have no idea what that temperature of that water is. So we're going to turn off the heater, we'll flash a code, say the thermistor is open, and we're just going to continue the cycle. We're going to circulate the water, but you're not going to get any hot water. Now on the same condition, look down here where it's shorted. So we don't want 5 volts coming in. So in that condition, if we see 5 volts are very near it, we know they're shorted. So again, we'll flash a code, or we'll put up some kind of blinking light, some kind of numerical code maybe. If you have a type of the dishwasher that gives you numbers, then it could put a code out there for that. And again, we do not want to turn on the heater because we have no idea what the temperature of the water is. But again, it'll go through the cycle. It'll wash your dishes, but of course the water's not going to be hot. It's not going to turn it on at the end of the drying cycle where you're trying to dry your dishes off. So that means that 0 volts and 5 volts is a condition that indicates a fault. So you can see that pretty much here's the range of voltages of where we want to be in for a normal dishwasher. Now let's take a look at it. The thermistor is good. And we're saying, well, dishwasher manufacturers usually want you to set your water heater to around 120 to 140 degrees. Okay, but let's say you turn yours down and it's, it's not that temperature coming in. And let's just say that it came in at, say 100 degrees. What if we look right here, we can see that's going to be 5.8 K on the resistor. And if we look at this, it's going to be 2.25 volts coming into the A to D converter. Well, in the program, I say, hey, if I see some voltage near 2.25, maybe 2 volts, I know that temperature of the water is not hot enough. So therefore, I'm going to turn on the heater to get that temperature up to 120 degrees. Usually that's what they run at, is 120 degrees thereabout for most of the cycles, unless they want to turn it up higher, maybe for a heavy duty wash. But let's say that it's going to go up to 120 degrees. So it's going to turn that heater on, and then the temperature of the water is going to be raised up. But keep in mind that thermistor is always measuring that temperature, so that resistance is going to change. So let's say it gets up to around 120. So here you can see that the resistance will drop from 5.8 K, where it was 100. Now it's dropped down to 3.4 K. At this point, it says, hey, Look at there. The voltage is rised up to 2.91 coming in. Now in the program, and using say if statements, if this voltage is in this range, I can say that is hot enough. Then at that point, I will turn off the heater because it doesn't need to be on because it's hot enough, the temperature of the water. Now if you like that circuit for as a thermistor, and you like working on cars, then you're probably familiar with engine coolant temp sensors and intake air temp sensors. They work exactly the same way as the circuit I just described with the dishwasher. In fact, I did a video on those two type sensors of how they work, and I'll do some working examples of showing of how these voltages change when the resistance change. If you're interested in seeing that, I'll put a link to that video in the description and you can take a look at it. Okay, so you check the thermistor circuit out, everything looks good. You still don't have no heated water to wash your dishes, or you see that the heater's not coming on. When you open it up at the end of the cycle, you got a bunch of water in there. You know, the heater never come on to dry. Okay, so now we're going to turn our attention over to the heater itself. Now here's the heater. So I got the dishwasher turned over. Here's the heater terminals right here. Now we're going to just check the resistance. So all you have to do is unplug one terminal. You don't have to unplug both. So just get one lead up on one of them terminal, come down here to the other one, see what our meter reading reads, and I got 16.3 ohms. You got anything in there thereabout, you're good to go. If you got an OL, you know you're screwed. If you got 0, you're screwed. Get a heater. All right. Now let's say you check that and everything looks good. Well, there is one other thing you can check, and that's going to be the thermal cutout switch. Now the thermal cutout switch is going to be right down here on the very bottom. If you follow this wire, and if you look right here, you can see this component. This is a high temperature thermostat. I think it's around about 180 degrees. It will trip if the heater gets too hot. Now this one has a manual reset. So if it does trip, you put your meter leads across it and it's open where it should be closed. You can come in here, you can push that button, and then that will manually reset it. It will not reset by itself. You actually have to push it in manually. And so that is another thing you can check. Now if that doesn't look, if everything looks good there, well then it's time to go ahead and get your meter on here. Now you're gonna have to put it in a cycle, you know, for a heat cycle, and you're gonna have to put your meter leads across here, see if you get your 120 volts. If you don't get your 120 volts, then you know you got a problem with the main control board. And by the way, the main control board is located right over in here, and you can drop that down by coming in the front cover. There's a couple of screws, one over here, one over here. Take them out and this whole board will drop down. So I think we covered it pretty good here. By the way, this is where the flood switch is located, right here. This is where a turbidity sensor would go. In my case, this dishwasher doesn't have one. This right here is the circulation pump. This right up here is the drain pump. And of course, we already mentioned there's the water inlet valve up there. And I mean, really, it's not much to this thing. Okay, we're at the end of the video. Was it too much? Not enough? Well, I thought about doing one more video and how we can look at some diagnostic modes that we can go into on the dishwasher to try to give us a direction of which way to go. Is it a latch switch? Is it a thermistor, turbidity sensor, main control board, user interface board? So you want to know kind of where to go. So we're going to save that video for the next one. And some people might say, well, why we have all this so much information? And the reason is I'm giving you as much information to make you a better troubleshooter, so you can find out what's wrong instead of ordering parts, putting them in, and it doesn't fix the problem. Because there's a lot of videos like I've seen on YouTube, people say order a heater, they don't check nothing, put it in, it doesn't work. Then they check the resistance and find out their old heater is good. And then they go back now to go, you know, change some other part. So the whole thing is to save you some money, make you more knowledgeable, make you a better troubleshooter. And if that doesn't work for you, then I say you got more money than I got, and I'm happy for you. So anyway, we're going to talk about these diagnostic modes in the next video. So you take care, and I'll see you in the next one.